A dying star is collapsing into a black hole and releasing more energy in 10 seconds than our sun will produce in its entire 10 billion year lifetime. We thought supernovae were the ultimate cosmic explosions. We were completely wrong. In 1967, American military satellites designed to detect nuclear weapons testing stumbled upon mysterious flashes of gamma radiation coming from deep space. These weren't bombs, they were something far more powerful. Scientists have discovered gamma-ray bursts, cosmic explosions so violent they can outshine entire galaxies containing hundreds of billions of stars. A single gamma-ray burst releases more energy in seconds than 1 trillion suns burning for 1 million years. To put this in perspective, if a gamma-ray burst occurred just 0 light years from Earth, practically next door in cosmic terms, it would appear as bright as the sun in our sky despite being thousands of times farther away. The energy release is so staggering that astronomers initially thought their instruments were malfunctioning. Dr. Ray Klebsiedl, who led the team that first identified these cosmic monsters in 1973, later described the discovery as finding something that shouldn't exist according to our understanding of physics. Tonight, we're going to explore the most energetic events in the universe. You will discover why a collapsing star can release more energy in moments than our sun will produce across geological time. We'll journey into the heart of stellar death, witness the birth of black holes, and understand how these cosmic lighthouses reshape our understanding of energy, time, and the very fabric of space itself. But here is what makes this truly mind-bending. Gamma-ray bursts don't just release incredible amounts of energy. They focus it into beams so intense they can sterilize planets from billions of light years away. We're talking about cosmic death rays that can end civilizations across galactic distances, powered by physics so extreme it challenges our fundamental understanding of matter and energy. The numbers alone are staggering. A typical gamma-ray burst releases Y joules of energy in its initial flash. That is a 1 followed by 44 zeros. To visualize this magnitude, imagine every star in our galaxy suddenly exploding simultaneously. That wouldn't even come close to the energy output of a single gamma-ray burst. NASA's SWIFT satellite and the Fermi Gamma-ray Space Telescope have detected these cosmic monsters occurring roughly once per day, somewhere in the observable universe, each one a testament to nature's ability to concentrate unimaginable power into fleeting moments of cosmic violence. Dr. Jonathan Granat from Ben-Gurion University, a leading expert on gamma-ray burst physics, explains that these events represent the most efficient conversion of matter into energy we've ever observed, far exceeding even nuclear fusion in stars or the annihilation of matter and antimatter. When we witness a gamma-ray burst, we're seeing the universe demonstrating physics at its most extreme limits. What makes this revelation particularly disturbing is the realization that our own galaxy likely experiences gamma-ray bursts, and Earth has probably been bathed in their radiation multiple times throughout geological history. Some scientists theorize that gamma-ray bursts may have triggered mass extinction events, fundamentally altering the course of evolution on our planet. The Ordovician extinction 450 million years ago, which eliminated 85% of marine species, bears the hallmarks of a gamma-ray burst sterilizing Earth's atmosphere. As you sit here right now reading these words, gamma-ray bursts are occurring across the cosmos. Stellar collapses, so violent they bend space-time itself, creating ripples in the gravitational fabric of reality, while simultaneously launching jets of pure energy at nearly the speed of light. These aren't just distant light shows. They're cosmic engines that forge the heaviest elements in the universe, seed space with the building blocks of planets, and potentially determine which regions of the cosmos can support complex life. The story of gamma-ray bursts is ultimately the story of energy itself, how matter can be converted into pure power with an efficiency that makes our sun look like a dying candle. It is a journey that will take us from the quantum mechanics of collapsing stellar cores to the large-scale structure of the universe, revealing how the most violent events in nature also serve as cosmic creators, forging the elements that make planets, stars, and ultimately, life itself possible. If you're fascinated by cosmic phenomena that defy imagination, subscribe and hit the thumbs up button. And here is a question that will haunt you. If gamma-ray bursts can sterilize entire star systems from across the galaxy, what does that mean for the likelihood of complex life existing elsewhere in the universe? Comment below with your thoughts. I'll pin the most thought-provoking response. Throughout this exploration, we'll discover exactly why a dying star can outshine entire galactic civilizations, how the laws of physics allow such impossible energy concentrations, and what gamma-ray bursts reveal about the ultimate fate of matter in our universe. We'll examine the cutting-edge research that's revolutionizing our understanding of stellar death, explore the implications for life across cosmic distances, and confront the profound questions these discoveries raise about our place in a universe where the most beautiful phenomena are often the most deadly. Now let's begin our journey into the heart of cosmic violence, where stars die with such fury they can illuminate the observable universe. Chapter 1. Cosmic explosions. The universe has a way of hiding its most violent secrets in plain sight. For billions of years, gamma-ray bursts have been detonating across the cosmos. Each one, a stellar death so catastrophic it releases more energy in seconds than entire galaxies produce over millennia. Yet until 5 decades ago, we had no idea these cosmic monsters even existed. The discovery began with paranoia, not science. During the Cold War, American military satellites scanned Earth's atmosphere for gamma rays, the telltale signature of nuclear weapons testing. The Vela satellites, launched between 1963 and 1970, were designed to detect Soviet violations of the Nuclear Test Ban Treaty. But on July 2, 1967, something unexpected happened. Vela 4 detected a massive burst of gamma radiation unlike anything in its programming. The signal wasn't coming from Earth. It wasn't even coming from our solar system. The gamma rays were arriving from deep space, carrying energy so extreme they suggested explosions powerful enough to vaporize planets. Dr. Ray Klebsadel and his team at Los Alamos National Laboratory spent 6 years analyzing the data before publishing their findings in 1973. They had inadvertently discovered the most energetic phenomenon in the known universe. What exactly is a gamma-ray burst? Imagine the most powerful nuclear weapon ever detonated, the Soviet Tsar Bomba, which released 50 megatons of energy in 1961. Now imagine an explosion that releases more energy than 10 billion trillion Tsar bombas detonating simultaneously every second for 10 seconds straight. That barely approaches the scale of a typical gamma-ray burst. The physics involved defies intuition. When certain massive stars reach the end of their lives, their cores collapse with such violence that matter compressed to nuclear density rebounds, launching jets of plasma at 99.99% the speed of light. These jets carry gamma rays, electromagnetic radiation so energetic that each photon contains millions of times more energy than visible light. Dr. Krissa Cavaliatu from George Washington University, whose research team classified gamma-ray bursts into short and long-duration events, describes the phenomenon as nature's ultimate particle accelerator, creating conditions more extreme than anything we could ever hope to replicate on Earth. The energy scales are genuinely staggering. A typical long-duration gamma-ray burst, lasting anywhere from several seconds to several minutes, releases approximately YY joules of energy. To put this in perspective, that is equivalent to converting the entire mass of our Sun into pure energy according to Einstein, S E = mc. But here is the crucial difference. Our Sun will spend 10 billion years gradually converting a tiny fraction of its mass into energy through nuclear fusion. A gamma-ray burst converts a significant portion of a star's rotational energy and magnetic field energy into directed radiation in mere moments. Consider the implications. The gamma-ray burst GRBO 80916C, detected by NASA's Fermi Gamma-ray Space Telescope on September 16, 2008, occurred 12.2 billion light-years away, when the universe was less than 2 billion years old. Despite this enormous distance, it was visible to instruments on Earth for 23 minutes, pumping out gamma rays with individual photon energies exceeding 13 billion electron volts. For comparison, visible light photons carry energies measured in electron volts, not billions of them. The directional nature of gamma-ray bursts makes them even more remarkable. Unlike supernova, which explode roughly spherically in all directions, gamma-ray bursts focus their energy into narrow jets typically spanning just 1 to 10 degrees of sky. This means we only detect gamma-ray bursts when their jets happen to point toward Earth, like cosmic lighthouses sweeping across the universe. Dr. Andrew McFadden from New York University, whose computer simulations helped explain the jet mechanism, calculates that for every gamma-ray burst we detect, there are roughly 500 others occurring at similar distances, but pointing in different directions. This geometric factor reveals something profound about energy distribution in the universe. If gamma-ray bursts radiate energy equally in all directions, their total energy output would be incomprehensible, approaching the binding energy that holds galaxies together. By concentrating their power into narrow beams, gamma-ray bursts become the most efficient energy delivery systems in the cosmos, capable of affecting matter across intergalactic distances. The detection process itself showcases human ingenuity in the face of cosmic extremes. Gamma rays cannot penetrate Earth's atmosphere, so all observations must be made from space-based observatories. The Burst Alert Telescope aboard NASA's Swift satellite can detect a gamma-ray burst and relay its coordinates to ground-based telescopes within 15 seconds, enabling rapid follow-up observations across the electromagnetic spectrum. This swift response capability has revolutionized our understanding of these events, revealing that gamma-ray bursts produce afterglows and X-rays, visible light and radio waves that can persist for weeks or months. The frequency of gamma-ray bursts adds another layer of cosmic perspective. Current estimates suggest that roughly 1 gamma-ray burst occurs somewhere in the observable universe every day. With approximately 100 billion galaxies in the observable universe, this means each galaxy experiences a gamma-ray burst roughly once every 300,000 years on average. Our own Milky Way galaxy, containing an estimated 400 billion stars, likely hosts a gamma-ray burst approximately every 100,000 to 1 million years. But here is what makes this frequency truly unsettling. Gamma-ray bursts can affect life across vast distances. A gamma-ray burst occurring anywhere within our galactic neighborhood, within roughly 8,000 light-years of Earth, could strip away significant portions of our ozone layer, exposing the planet's surface to lethal ultraviolet radiation from the sun. The energy densities involved are so extreme that even at these distances, the gamma-ray flux would exceed that of a major solar flare by factors of thousands. The discovery of gamma-ray bursts fundamentally changed our understanding of stellar death. Before 1967, astronomers thought supernova represented the ultimate expression of stellar violence. These stellar explosions, bright enough to outshine entire galaxies for weeks, seemed to represent the upper limit of cosmic energy release. Gamma-ray bursts revealed that nature had far more violent processes in reserve. Stellar deaths so catastrophic they make supernova appear gentle by comparison. This revelation raises profound questions about the evolution of the universe itself. If gamma-ray bursts have been occurring throughout cosmic history, they may have played crucial roles in determining which regions of space could support the development of complex life. Dr. Brian Thomas from Washburn University has calculated that gamma-ray bursts could effectively sterilize large volumes of space, creating dead zones where life cannot emerge or survive for millions of years following each burst. As we continue exploring the nature of these cosmic explosions, we'll discover that gamma-ray bursts represent more than just stellar death. They're cosmic factories, forging the heaviest elements in the universe and distributing them across intergalactic space. The same processes that make them so destructively powerful also make them essential for the chemical evolution of the cosmos. Every atom of gold, platinum, and uranium on Earth may have been forged in the heart of a gamma-ray burst billions of years ago. The story of cosmic explosions is ultimately a story about the universe's capacity for extremes. How the same physical laws that govern the gentle fusion reactions in our Sun can also drive stellar collapses so violent they reshape the fabric of space-time itself. Chapter 2. Hidden Violence. The universe conceals its most extreme violence behind vast distances and the limitations of human perception. What appears as a brief flicker in our most sensitive instruments represents stellar death throes so violent they challenge our understanding of physics itself. The hidden nature of gamma-ray burst violence lies not just in their remote locations, but in the impossible energies they unleash through mechanisms that remain mysterious for decades after their discovery. The breakthrough in understanding came in 1998 with the detection of gamma-ray burst afterglows, fading emissions that persist long after the initial blast. The Beppo-SAX satellite, an Italian-Dutch X-ray observatory, detected GRB 970,228 and, for the first time, provided accurate enough coordinates for ground-based telescopes to identify the burst's host galaxy. Dr. Jan van Paradijs from the University of Amsterdam, who led the Afterglow discovery team, described the moment as finally seeing the scene of the crime. The host galaxy was located 8 billion light-years away, confirming that gamma-ray bursts originated from cosmological distances. This distance measurement revealed the true scale of hidden violence. If a gamma-ray burst could be detected across 8 billion light-years, roughly half the radius of the observable universe, the energy output had to be incomprehensibly vast. Dr. Bohdan Pachivsky from Princeton University calculated that gamma-ray bursts must release more energy than any other known phenomenon except the Big Bang itself. The implications were staggering. We were witnessing explosions that could be seen from the edge of the visible cosmos. The violence begins in the final moments of a massive star's life. Stars with masses exceeding 25 to 30 times our Sun face a catastrophic fate that differs fundamentally from the peaceful stellar death we observe in our Sun's future. When nuclear fusion can no longer support the star against gravitational collapse, the core implodes with devastating speed. In less than 1 second, a stellar core larger than Earth compresses to a sphere roughly 20 kilometers in diameter, reaching densities exceeding 100 trillion kilograms per cubic meter. The violence of this collapse defies description. Imagine every atom of matter on Earth, approximately Y atoms suddenly compressed into a space the size of Manhattan. The gravitational forces involved are so extreme they warp space-time itself, creating conditions where the normal rules of physics begin to break down. Dr. Stan Woosley from the University of California, Santa Cruz, whose computer simulations model these stellar collapses, describes the process as the most violent event that can occur in nature, short of the formation of the universe itself. But collapse is only the beginning of the violence. As the stellar core reaches nuclear density, it suddenly stiffens, causing the unfolding material to rebound in a shock wave that attempts to propagate outward through the star. In most cases, this shock wave stalls, unable to overcome the continued gravitational infall. However, in gamma-ray burst progenitors, rapid rotation and intense magnetic fields combine to launch twin jets of material at velocities approaching 99.99% the speed of light. These jets represent violence concentrated to an almost unimaginable degree. The material within the jets experiences acceleration forces exceeding 10-12 times Earth's gravity, pressures that would compress human tissue to the density of atomic nuclei. Dr. Ramesh Narayan from Harvard University, whose theoretical work explained the jet formation mechanism, calculates that the magnetic field energies involved exceed 1,015 times the strength of Earth's magnetic field, creating conditions where matter behaves more like pure energy than conventional particles. The hidden aspect of this violence lies in its efficiency. Unlike a supernova explosion, which converts only about 1% of the star's rest mass energy into kinetic energy, gamma-ray bursts can convert up to 50% of their progenitor star as rotational and magnetic energy into directed radiation. This efficiency approaches the theoretical maximum predicted by general relativity for energy extraction from rotating black holes through the Penrose process, suggesting that gamma-ray bursts represent nature operating at the absolute limits of physical possibility. The gamma rays themselves carry the signature of this extreme violence. Each photon possesses energies measured in millions to billions of electron volts, compared to the 2 to 3 electron volts of visible light photons. These high-energy gamma rays are produced when electrons accelerated to near-light speeds interact with the intense magnetic field surrounding the jets, a process called synchrotron radiation. Dr. Peter Masharos from Pennsylvania State University, a pioneer in gamma-ray burst theory, describes these conditions as natural particle accelerators more powerful than any human technology could ever achieve. The violence extends beyond the immediate vicinity of the dying star. As the gamma-ray jet propagates outward, it sweeps up interstellar material, creating a bow shock that can accelerate particles to cosmic ray energies. These cosmic rays, atomic nuclei moving at near-light speeds, carry the violence of gamma-ray bursts across galactic distances, potentially affecting planetary atmospheres thousands of light-years away from the original explosion. Perhaps most remarkably, the violence occurs within a framework of precise physics. Despite the extreme conditions, gamma-ray bursts follow predictable patterns governed by well-understood physical laws. The relationship between burst duration, energy output, and spectral characteristics reveals underlying mathematical relationships that suggest even the universe, as most violent events, operate according to fundamental principles. Dr. Enrico Ramirez Ruiz from the University of California, Santa Cruz, whose research focuses on the diversity of gamma-ray burst progenitors, notes that even in the most chaotic stellar death, we see the elegant hand of physics imposing order on apparent violence. The hidden nature of gamma-ray burst violence also manifests in their temporal structure. What appears as a single burst to our instruments often consists of multiple subbursts, each representing a separate episode of energy release. High-resolution observations reveal structure on timescales as short as milliseconds, suggesting that the central engine, likely a newly formed black hole, undergoes rapid fluctuations in accretion rate or magnetic field configuration. These rapid variations indicate violence occurring on scales where general relativistic effects become dominant. The violence is not uniformly distributed in space or time. Long-duration gamma-ray bursts, lasting more than 2 seconds, occur preferentially in star-forming regions of young, metal-poor galaxies, where massive stars can maintain the rapid rotation necessary for jet formation. Short-duration bursts lasting less than 2 seconds result from the merger of neutron, stars or black holes events that can occur in any galactic environment, but release their violence through different mechanisms involving the collision of objects each containing more mass than our Sun, compressed into city-sized spheres. The discovery of gravitational waves has added another dimension to our understanding of hidden violence. The LIGO-Virgo collaboration's detection of gravitational waves from neutron star mergers, combined with simultaneous gamma-ray observations, revealed that these cosmic collisions produce both spacetime ripples and electromagnetic radiation. The violence of these mergers is sufficient to synthesize gold, platinum, and other heavy elements through rapid neutron capture processes, suggesting that the universe's most violent events also serve as cosmic alchemists. The implications of hidden violence extend to the fundamental structure of the universe. Gamma-ray bursts may have played crucial roles during the cosmic dark ages, the period between the formation of the first stars and the reionization of intergalactic hydrogen. Dr. Abraham Loeb from Harvard University has proposed that gamma-ray bursts could have been among the first sources of ionizing radiation in the early universe, their violence helping to clear the cosmic fog that obscured the first billion years of cosmic evolution. As we probe deeper into the mechanisms of gamma-ray burst violence, we encounter phenomena that push our understanding of physics to its limits. The observation of gamma-ray photons with energies exceeding 100 billion electron volts from some bursts suggests acceleration mechanisms that may require exotic physics, possibly involving the interaction of matter with the black hole's event horizon itself. This hidden violence shapes our cosmic perspective in profound ways. Every gamma-ray burst represents a star that died with such fury it could outshine billions of ordinary stellar deaths combined. The energy released in seconds exceeds what our civilization has produced throughout all of human history by factors that strain comprehension. Yet this violence is also creative, forging elements essential for planet formation and distributing them across cosmic distances. Chapter 3. Stellar Comparison. To truly grasp the magnitude of gamma-ray burst energy release, we must place it in the context of stellar power sources we can more easily comprehend. Our Sun, a middle-aged star of perfectly ordinary specifications, provides the baseline for understanding cosmic energy production. What we discover through this comparison reveals not just the scale of gamma-ray bursts, but the fundamental limits of how matter can be converted into energy across cosmic time. Our Sun converts approximately 4.3 million tons of mass into energy every second through nuclear fusion, following Einstein's famous equation E equals mc. This process, occurring at the Sun's core, where temperatures reach 15 million Kelvin, transforms hydrogen nuclei into helium, while releasing 3.8 times watts of power continuously. Dr. John Bacall from the Institute for Advanced Study, whose solar neutrino experiments confirmed our understanding of stellar fusion, calculated that our Sun has maintained this energy output for 4.6 billion years and will continue for another 5 billion years. The cumulative energy output is staggering by human standards. Over its entire 10 billion year main sequence lifetime, our Sun will convert roughly 0.7% of its total mass into energy, releasing approximately 1.2 times joules. This represents the complete nuclear fuel supply available through hydrogen fusion, the most efficient energy source available to normal stellar evolution. Every joule our Sun produces requires the careful orchestration of quantum tunneling effects that allow hydrogen nuclei to overcome electromagnetic repulsion and fuse into heavier elements. Now consider the violence of stellar comparison. A typical long-duration gamma-ray burst releases YY to YY joules in its initial gamma-ray emission alone, equivalent to our Sun's entire lifetime energy output concentrated into seconds or minutes. GRBO 80916c, detected by the Fermi Gamma-ray Space Telescope, released an estimated 8.8 times joules in gamma rays over its 23-minute duration, effectively matching our Sun's total energy budget while operating with an efficiency that dwarfs stellar fusion. The comparison becomes even more remarkable when we consider stellar mass scales. The progenitor stars of gamma-ray bursts typically contain 25 to 100 times more mass than our Sun, providing vastly larger energy reservoirs. Yet they convert this mass into directed energy through mechanisms that operate billions of times faster than stellar fusion. Dr. Enrico Ramirez Ruiz, from UC Santa Cruz, whose research focuses on massive star evolution, notes that gamma-ray burst progenitors represent stellar death so violent it makes our Sun's peaceful fusion appear almost static by comparison. The efficiency differences reveal fundamental physics. Solar fusion operates at approximately 0.7% mass-to-energy conversion efficiency, limited by the binding energy differences between hydrogen and helium nuclei. Gamma-ray bursts can achieve effective conversion efficiencies approaching 50% for their available rotational and magnetic energy, utilizing mechanisms that tap into the gravitational binding energy of stellar collapse and the rotational energy of rapidly spinning black holes. To visualize this stellar comparison, imagine our Sun suddenly gaining the ability to release its entire 10 billion year energy output in 10 seconds. The Earth would be vaporized instantly, the solar system would be sterilized out to Neptune's orbit, and the explosion would be visible from neighboring galaxies. This thought experiment approximates the energy release of a single gamma-ray burst. Except the actual phenomenon operates through physical processes our Sun could never access. The temporal comparison is equally striking. Our Sun produces energy through a delicate balance of gravitational compression and radiation pressure, maintaining stable fusion for billions of years through precise equilibrium. Gamma-ray burst progenitors abandon this stability in favor of catastrophic energy release. The stellar core collapse that triggers gamma-ray burst formation occurs in less than 1 second, during which gravitational potential energy, equivalent to thousands of years of solar output, gets converted into kinetic energy of the collapsing material. The spectral comparison reveals another dimension of the stellar energy divide. Our Sun emits most of its energy as visible and infrared light, with peak emission at wavelengths around 500 nanometers, the green portion of the spectrum. Gamma-ray bursts emit their energy as gamma rays with wavelengths shorter than 0.01 nanometers, representing photons millions of times more energetic than solar radiation. Dr. Neil Gehrels, former principal investigator for NASA's SWIFT satellite, observed that comparing solar radiation to gamma-ray burst emission is like comparing a candle to a nuclear explosion. The energy per photon differs by factors that challenge our ability to visualize. The directional aspect of stellar comparison adds yet another layer of magnitude. Our Sun radiates energy isotropically, equally in all directions, with Earth receiving only about 1/2 billionth of the total solar output. Gamma-ray bursts concentrate their energy into narrow jets, creating energy densities millions of times higher than if the same energy were distributed spherically. A gamma-ray burst jet aimed at Earth from within our galaxy would deliver energy fluxes exceeding solar radiation by factors of millions, despite originating from much greater distances. The elemental forging comparison reveals the creative potential hidden within destructive processes. Our Sun will eventually produce carbon, nitrogen, and oxygen through helium fusion during its red giant phase, but it lacks the mass necessary to forge elements heavier than oxygen. Gamma-ray bursts and their associated supernova synthesize elements up to and beyond iron through explosive nucleosynthesis, while their neutron-rich environments enable rapid neutron capture processes that create gold, platinum, and uranium. Dr. Jennifer Johnson from Ohio State University, whose research traces elemental abundances in stellar populations, calculates that single gamma-ray burst events can produce more heavy elements in minutes than entire generations of solar mass stars create over billions of years. The stellar comparison extends to evolutionary timescales. Our Sun formed from a molecular cloud enriched by previous generations of massive stars, inheriting approximately 2% of its mass in elements heavier than hydrogen and helium. The progenitor stars of gamma-ray bursts evolve much more rapidly, completing their entire life cycles in just a few million years compared to our Sun's 10 billion year lifetime. This rapid evolution means gamma-ray burst progenitors experience nuclear burning phases that our Sun will never reach, accessing fusion reactions that produce increasingly heavy elements, until nuclear burning can no longer support the star against gravitational collapse. The magnetic field comparison reveals another aspect of stellar extremes. Our Sun maintains magnetic field strengths of approximately 1 Gauss at its surface, occasionally producing solar flares that release 1,025 joules of energy, enough to power human civilization for thousands of years. Gamma-ray burst progenitors can maintain magnetic field strengths exceeding YP Gauss, creating magnetospheric conditions where matter behaves according to quantum electrodynamic effects that transform the very nature of atomic structure. The rotational energy comparison provides insight into the power sources that enable such extreme energy release. Our Sun rotates with a period of 27 days at its equator, containing rotational kinetic energy of approximately 1,042 joules. Gamma-ray burst progenitors can rotate with periods of milliseconds, storing rotational energies exceeding 1045 joules, energy reservoirs that can be tapped through magnetic braking and gravitational collapse to power the observed gamma-ray emission. The stellar comparison ultimately reveals that gamma-ray bursts represent physics operating at the absolute limits of possibility within our universe. While our Sun demonstrates the steady, reliable energy production that enables planetary habitability over geological time, gamma-ray bursts showcase nature's capacity for energy release. So extreme, it approaches the theoretical maximum predicted by general relativity. Dr. Bing Zhang from the University of Nevada, Las Vegas, whose research focuses on gamma-ray burst central engines, observes that the stellar comparison shows us both the gentle face of nuclear physics that enables life and the violent face that can reshape entire galactic neighborhoods in moments. This comparison sets the stage for understanding how gamma-ray bursts achieve their impossible energy outputs through mechanisms that transcend normal stellar evolution. Chapter 4. Energy Mechanics. The mechanisms that enable gamma-ray bursts to release more energy than our Sun's entire lifetime output in mere moments operate at the intersection of general relativity, quantum physics, and magnetohydrodynamics. Understanding these energy mechanics requires exploring physical processes so extreme they challenge our everyday intuition about how matter and energy interact under the universe's most violent conditions. The energy source begins with gravitational binding energy, the potential energy stored in the gravitational field of a massive object. For a star with 30 times the Sun's mass, the total gravitational binding energy approaches 1,046 joules, roughly 10 times our Sun's entire lifetime energy output. Dr. Kip Thorne from Caltech, whose work on relativistic astrophysics earned him a Nobel Prize, explains that gravitational collapse represents nature's most efficient method for concentrating energy capable of accessing binding energies that dwarf nuclear processes by orders of magnitude. The collapse mechanics begin when nuclear fusion can no longer support the stellar core against gravity. The core, containing roughly 1.5 solar masses compressed into a sphere the size of Earth, becomes unstable and collapses at velocities approaching 30,000 kilometers per second, roughly 10% the speed of light. During this collapse, gravitational potential energy converts into kinetic energy with devastating efficiency. Dr. Adam Burrows from Princeton University, whose computer simulations model core collapse supernova, calculates that the energy released during stellar core collapse exceeds the kinetic energy of the entire Earth's orbital motion by factors of millions. The formation of a proton-neutron star, or black hole, provides the central engine that powers gamma-ray burst energy release. When the collapsing core reaches nuclear density, approximately 1,015 kilograms per cubic meter, it suddenly stiffens, causing infalling material to rebound in a shock wave. However, in gamma-ray burst progenitors, this shock wave alone cannot explain the observed energy output. The key lies in the extraction of rotational energy from rapidly spinning black holes through the Blandford-Znayak mechanism. The Blandford-Znayak mechanism, proposed by Roger Blandford and Roman Znayak in 1977, describes how rotating black holes can power relativistic jets through magnetic field interactions. When a black hole spins, it drags spacetime itself through a process called frame dragging, creating an ergosphere where stationary observers cannot exist. Magnetic field lines threading this region become twisted, storing energy that can be extracted to power jets of relativistic plasma. Dr. Roger Blandford from Stanford University, co-discoverer of this mechanism, describes it as nature's ultimate dynamo, capable of converting the rotational energy of black holes into directed electromagnetic energy with remarkable efficiency. The energy extraction efficiency depends critically on black hole spin rate and magnetic field strength. A maximally rotating black hole can theoretically convert up to 42% of its rest mass energy into jet power through the Blandford's Nyack process. For a 10 solar mass black hole, this represents approximately 1045 joules of available energy, 4 times our Sun's lifetime output accessible through magnetic field interactions with the spinning spacetime geometry. The magnetic field amplification occurs through magnetorotational instability in the accretion disk surrounding the newly formed black hole. As stellar material falls toward the black hole, differential rotation creates turbulence that amplifies magnetic fields through dynamo processes. Dr. Stephen Balbus from Oxford University, whose work on magnetorotational instability earned widespread recognition, calculates that magnetic field strengths can increase by factors of y to 108 during the accretion process, creating conditions where magnetic pressure can dominate gas pressure and drive powerful outflows. The jet formation mechanism concentrates this extracted energy into narrow beams through magnetohydrodynamic processes operating in the extreme gravitational environment near the black hole. The magnetic field lines, anchored in the accretion disk and stretched by the rotating black hole, create a magnetic bottle that collimates the outflowing plasma into jets with opening angles typically spanning 110 degrees. Dr. Jonathan McKinney from the University of Maryland, whose general relativistic magnetohydrodynamic simulations model these processes, explains that the jet formation represents a delicate balance between magnetic pressure, gas pressure, and gravitational forces operating in the curved spacetime near rotating black holes. The acceleration mechanics within the jets involve multiple physical processes operating simultaneously. Magnetic acceleration dominates near the black hole, where strong magnetic fields can accelerate particles to relativistic speeds through magnetic reconnection events. As the jet propagates outward, radiation pressure from gamma-ray photons can provide additional acceleration, while internal shocks created by variations in the central engine power create the observed gamma-ray variability. Dr. Anatoly Spitkovsky from Princeton University, whose particle and cell simulations model relativistic shock acceleration, notes that gamma-ray burst jets represent natural particle accelerators operating at energies we could never hope to achieve in terrestrial laboratories. The gamma-ray production mechanisms involve both synchrotron radiation and inverse Compton scattering in the relativistic shock environment. High-energy electrons accelerated to near-light speeds emit synchrotron radiation when they encounter magnetic fields, producing gamma rays with characteristic power law energy spectra. Additionally, lower-energy photons can be upscattered to gamma-ray energies when they interact with relativistic electrons through inverse Compton processes. Dr. Frederick Dane from Sorbonne University, whose research focuses on gamma-ray burst emission mechanisms, calculates that the combination of synchrotron and inverse Compton processes can account for gamma-ray luminosities exceeding Y watts, sustained for tens of seconds through continued energy injection from the central black hole. The energy thermalization involves complex interactions between radiation, magnetic fields, and relativistic particles. The gamma-ray burst environment contains energy density so extreme that radiation pressure dominates over gas pressure, creating conditions where photons and particles exchange energy rapidly through Thomson scattering. This radiation-dominated regime rarely encountered in normal astrophysical environments, enables the efficient conversion of kinetic energy into gamma-ray emission. Dr. Andrei Beloborov from Columbia University, whose theoretical work addresses gamma-ray burst radiative processes, observes that the energy thermalization in gamma-ray bursts occurs under conditions where quantum electrodynamic effects become important, potentially modifying the interaction between matter and radiation. The temporal energy release pattern reveals the underlying mechanics of the central engine. Long-duration gamma-ray bursts typically show erratic variability on timescales ranging from milliseconds to hundreds of seconds, suggesting that the black hole accretion rate fluctuates dramatically during the burst. These variations may result from instabilities in the accretion disk, variations in magnetic field configuration, or episodic injection of material into the black hole. Dr. Ramesh Narayan from Harvard University, whose work on black hole accretion flows spans decades, explains that the temporal structure of gamma-ray bursts provides a window into the physics of black hole formation and the early evolution of rapidly accreting black hole systems. The energetics of short-duration gamma-ray bursts involve different mechanics but comparable energy scales. These events, lasting less than 2 seconds, result from the merger of neutron stars or neutron-star black hole binaries. The collision and merger process releases gravitational binding energy comparable to stellar core collapse, while the formation of accretion disks around the resulting black hole can power jets through similar magnetohydrodynamic processes. Dr. Ido Berger from Harvard University, whose observational work helped establish the neutron-star merger origin of short gamma-ray bursts, notes that compact object mergers represent the ultimate expression of gravitational energy release, capable of converting nuclear binding energy into electromagnetic radiation with remarkable efficiency. The energy conservation constraints provide crucial tests of gamma-ray burst models. The total energy output must be consistent with the available energy sources in the progenitor system, while the observed spectral characteristics must match predictions from relativistic shock acceleration and radiation transport models. Dr. Pawan Kumar from the University of Texas at Austin, whose analytical work provides foundational understanding of gamma-ray burst energetics, calculates that the energy conservation requirements favor models where gamma-ray bursts tap into the rotational energy of rapidly spinning black holes, as this provides the only energy reservoir sufficient to explain the most luminous observed events. The energy mechanics of gamma-ray bursts ultimately demonstrate how the universe's most extreme physical conditions enable energy release processes that transcend normal stellar evolution by factors of millions. Chapter 5. Universal beacons. Gamma-ray bursts serve as cosmic lighthouses. Their intense beams of radiation piercing through intergalactic space to reach observers across the observable universe. These universal beacons operate with such extraordinary luminosity that they can be detected from distances where entire galaxies appear as mere points of light, providing unique insights into cosmic evolution, star formation, and the fundamental structure of spacetime itself. The beacon-like nature of gamma-ray bursts results from their highly collimated emission. Unlike supernova, which radiate energy roughly equally in all directions, gamma-ray bursts focus their energy into narrow jets typically spanning 1 to 10 degrees of solid angle. Dr. Enrico Ramirez Ruiz from UC Santa Cruz, whose research helped establish the jet model for gamma-ray bursts, explains that this collimation effect increases the apparent luminosity by factors of 100 to 1000 compared to isotropic emission, enabling gamma-ray bursts to outshine entire galaxies despite originating from single stellar deaths. The extreme luminosities achieved through this beaming effect place gamma-ray bursts among the most powerful electromagnetic phenomena in the universe. GRBO 80319b, detected on March 19, 2008, reached a peak luminosity of 3 watts, roughly 2.5 million times more powerful than our entire galaxy's total energy output. Despite occurring 7.5 billion light-years away, this burst briefly became visible to the naked eye, achieving an apparent magnitude of 5.8. Dr. Judith Rakison from NASA Goddard Space Flight Center, who led the analysis of this remarkable event, observed that, for 30 seconds, a single dying star located halfway across the observable universe outshone every other point source in the night sky except the Moon and planets. The universal beacon properties enable gamma-ray bursts to probe cosmic evolution across unprecedented timescales, because their enormous luminosities make them detectable at cosmological distances. Gamma-ray bursts serve as probes of the early universe when galaxies were young and stellar populations differed dramatically from those observed today. GRB090423, discovered by NASA's SWIFT satellite, occurred when the universe was only 630 million years old, just 4.6% of its current age. Dr. Niall Tanvir from the University of Leicester, who led the team that determined this burst distance, notes that gamma-ray bursts provide our most direct observational access to the era of first stars, enabling studies of stellar death processes that occurred when the universe contained a fundamentally different mix of elements. The beacon mechanism depends on relativistic beaming effects that approach the theoretical limits predicted by special relativity. Gamma-ray burst jets typically achieve bulk Lorentz factors exceeding 100, meaning the jet material moves at velocities greater than 99.99% the speed of light. At these extreme velocities, relativistic effects dramatically enhance the observed luminosity through Doppler boosting. Radiation emitted in the direction of motion appears brighter and shifted to higher frequencies for stationary observers. Dr. Jonathan Granite from Ben-Gurion University, whose theoretical work addresses relativistic shock dynamics, calculates that Doppler boosting can increase the apparent gamma-ray luminosity by factors of YY to YY, explaining how stellar-scale explosions can appear brighter than entire galactic populations. The temporal structure of these universal beacons reveals the complex physics operating within relativistic jets. High-resolution observations show that individual gamma-ray bursts often consist of multiple subpulses separated by intervals ranging from milliseconds to seconds. This variability suggests that the central engine undergoes rapid fluctuations in accretion rate or magnetic field configuration, possibly reflecting instabilities in the black hole magnetosphere or episodic injection of material into the accretion flow. Dr. Krissa Kuvelia from George Washington University, whose research established a temporal classification system for gamma-ray bursts, explains that the rapid variability observed in gamma-ray burst-like curves provides direct evidence for the compact nature of the central engine, consistent with black hole or neutron star scales, rather than larger stellar structures. The spectral properties of these beacons encode information about the extreme physical conditions within relativistic jets. Gamma-ray burst spectra typically exhibit a characteristic peak around 100 keV to 1 MeV, with power law tails extending to lower and higher energies. This spectral shape, known as the band function after its discoverer Dr. David Band, reflects the complex interplay between synchrotron radiation from relativistic electrons and Compton scattering processes in the radiation-dominated environment near the jet. Dr. Felix Ride from the KTH Royal Institute of Technology, whose work addresses gamma-ray burst spectral evolution, observes that the spectral hardness and evolution patterns provide crucial constraints on magnetic field strengths, particle energies, and optical depths within the emission region. The polarization properties of gamma-ray burst beacons offer additional insights into the magnetic field structure within relativistic jets. Recent observations by the Icarus spacecraft detected significant linear polarization in the gamma-ray emission from GRB1 21024A, indicating that magnetic fields within the jet maintain coherent structure over scales comparable to the emission region. Dr. Shinji Nakamura from Nagoya University, who led this polarization study, notes that the detection of polarized gamma-ray emission confirms that magnetic fields play crucial roles in both jet acceleration and radiation production, supporting magnetohydrodynamic models for gamma-ray burst central engines. The afterglow properties transform gamma-ray bursts into long-lived beacons observable across the electromagnetic spectrum. As the relativistic jet interacts with surrounding material, it drives external shocks that accelerate particles and produce synchrotron emission spanning radio, optical, and X-ray wavelengths. These afterglows can persist for weeks to months, providing extended opportunities for detailed observations. Dr. Ido Berger from Harvard University, whose afterglow observations helped establish the cosmological distance scale for gamma-ray bursts, explains that afterglow studies enable precise localizations and host galaxy identifications, transforming gamma-ray bursts from mysterious flashes into powerful probes of cosmic star formation and galaxy evolution. The beacon effect enables gamma-ray bursts to serve as cosmic standard candles for probing dark energy and the expansion history of the universe. Because gamma-ray bursts can be detected at higher redshifts than Type Ia supernova, they potentially extend the cosmological distance ladder to epochs when the universe was dominated by dark energy. Dr. Giancarlo Galanda from INA Fabra Observatory, whose research focuses on gamma-ray burst luminosity correlations, has identified empirical relationships between peak luminosity, spectral lag, and variability that may enable standardization of gamma-ray burst distances. However, he cautions that the standardization of gamma-ray bursts as cosmological probes requires careful understanding of selection effects and the diversity of progenitor populations across cosmic time. The multi-messenger beacon properties of gamma-ray bursts became dramatically apparent with the detection of gravitational waves from neutron star merges. GW170817, detected by LIGO Virgo on August 17, 2017, was followed 1.7 seconds later by GRB 170817, detected by the Fermi Gamma-ray Space Telescope. This remarkable coincidence confirmed that short gamma-ray bursts can result from neutron star mergers, while demonstrating that these events produce both space-time ripples and electromagnetic beacons. Dr. Julie McHenry from NASA Goddard Space Flight Center, project scientist for the Fermi mission, observed that the multi-messenger detection opens entirely new possibilities for studying fundamental physics under extreme conditions. From testing general relativity to understanding the synthesis of heavy elements, the beacon network formed by gamma-ray bursts enables studies of the intergalactic medium and cosmic magnetic fields. As gamma-ray burst photons propagate across cosmological distances, they interact with intervening matter and magnetic fields, providing information about the large-scale structure of the universe. High-energy gamma rays can be absorbed through pair production interactions with the extragalactic background light, while polarization measurements can probe magnetic fields in galaxy clusters and filaments. Dr. Avery Broderick from the University of Waterloo, whose research addresses gamma-ray propagation effects, notes that gamma-ray bursts serve as background sources for studying the universe's magnetic field structure, potentially revealing signatures of primordial magnetic fields generated during cosmic inflation. The beacon luminosity function reveals the cosmic evolution of massive star formation rates across the observable universe. Because long-duration gamma-ray bursts result from the deaths of very massive stars, their rate of occurrence traces the formation rate of stars exceeding 25 to 30 solar masses throughout cosmic history. Dr. Peter Jacobson from the FIVES, University of Iceland, whose surveys probe gamma-ray burst rate evolution, has found evidence that the gamma-ray burst rate peaks at redshifts around 2 to 3, corresponding to the epoch of maximum cosmic star formation when the universe was 2 to 4 billion years old. The universal beacon properties of gamma-ray bursts ultimately reveal them as cosmic laboratories where the laws of physics operate under the most extreme conditions accessible to observation. Each burst represents a natural experiment in general relativity, quantum field theory, and magnetohydrodynamics that cannot be replicated in terrestrial laboratories. Chapter 6. Galactic Consequences. The consequences of gamma-ray bursts extend far beyond their immediate stellar environments, reshaping entire galactic neighborhoods through processes that can sterilize planetary systems, trigger star formation, and fundamentally alter the chemical composition of interstellar space. These galactic-scale effects reveal gamma-ray bursts as agents of both destruction and creation, capable of influencing cosmic evolution across scales spanning millions of light-years. The immediate galactic consequence of a gamma-ray burst involves the deposition of enormous energy into surrounding interstellar material. When the relativistic jet propagates outward from the dying star, it sweeps up ambient gas and dust, creating a bow shock that can extend for thousands of light-years. Dr. Brian Metzger from Columbia University, whose research addresses the environmental effects of gamma-ray bursts, calculates that a typical gamma-ray burst deposits approximately Y joules into its surrounding medium, enough energy to create superbubbles comparable to those formed by entire stellar associations over millions of years. The shock wave propagation creates cavities in the interstellar medium that can persist for millions of years after the initial burst. These gamma-ray burst bubbles, expanding at velocities exceeding 1,000 kilometers per second, compress surrounding material and trigger secondary shock waves that propagate across galactic distances. Dr. Mordecai Mark Mack, Lowe from the American Museum of Natural History, whose hydrodynamic simulations model these large-scale effects, explains that gamma-ray burst explosions can create interconnected networks of hot, low-density regions that fundamentally alter gas flows and stellar feedback processes throughout entire galactic disks. The sterilization effects represent perhaps the most dramatic galactic consequence of gamma-ray bursts. The intense flux of gamma rays can strip atmospheric ozone from planets located thousands of light-years away, exposing surface life to lethal ultraviolet radiation from their host stars. Dr. Adrian Mellett from the University of Kansas, whose research examines the biological effects of astrophysical radiation, has calculated that a gamma-ray burst occurring within 8,000 light-years of Earth could reduce stratospheric ozone concentrations by 35% or more, creating conditions comparable to nuclear winter scenarios but persisting for decades. The atmospheric chemistry modifications extend beyond ozone depletion to include the formation of nitrogen oxides and other photochemical pollutants. High-energy gamma rays interact with atmospheric nitrogen and oxygen molecules, creating cascades of secondary particles that can alter atmospheric composition for extended periods. Dr. Dimitra Autry from the NYU Center for Space Science, whose models address atmospheric photochemistry under extreme radiation conditions, notes that the chemical modifications caused by gamma-ray bursts can persist long after the initial radiation pulse, potentially affecting planetary habitability for thousands of years through altered atmospheric chemistry and climate patterns. The mass extinction correlations suggest that gamma-ray bursts may have played crucial roles in Earth's biological history. The Ordovician-Silurian extinction event 445 million years ago, which eliminated approximately 85% of marine species, shows characteristics consistent with atmospheric ozone depletion and subsequent ultraviolet radiation exposure. Dr. Peter Ward from the University of Washington, whose paleontological research addresses extinction mechanisms, observes that the biological signatures of the late Ordovician extinction, preferential elimination of surface-dwelling marine organisms and preservation of deep-water species, match predictions for gamma-ray burst-induced atmospheric damage, The galactic star formation consequences reveal the creative aspects of gamma-ray burst violence. The compression of molecular clouds by gamma-ray burst shock waves can trigger gravitational collapse and initiate new episodes of stellar birth. Dr. Mark Krumholz from the Australian National University, whose theoretical work addresses triggered star formation, calculates that gamma-ray burst explosions can compress molecular cloud cores beyond the threshold for gravitational instability, potentially increasing local star formation rates by factors of 10 to 100 for several million years following the burst. The chemical enrichment effects demonstrate how gamma-ray bursts serve as cosmic alchemists, synthesizing and distributing heavy elements throughout galactic environments. The rapid neutron capture processes operating during the burst create elements heavier than iron, including gold, platinum, and uranium. These R-process elements, ejected at high velocities during the explosion, can contaminate molecular clouds across kiloparsec scales. Dr. Anna Frebel from MIT, whose stellar archaeology traces the chemical evolution of the early universe, explains that gamma-ray bursts may have been the primary source of R-process elements in the early universe, when the heavy element abundance patterns we observe in metal-poor stars were first established. The magnetic field amplification represents another significant galactic consequence of gamma-ray burst activity. The turbulent motions generated by shock wave propagation can amplify interstellar magnetic fields through dynamo processes, creating magnetized regions that influence subsequent star formation and cosmic ray propagation. Dr. Ellen Zweibel from the University of Wisconsin-Madison, whose research addresses astrophysical magnetic field generation, notes that gamma-ray burst explosions can increase local magnetic field strengths by factors of 10 to 100, creating conditions that alter charged particle transport and modify the properties of molecular cloud collapse. The cosmic ray acceleration consequences extend the gamma-ray burst influence across entire galactic volumes. The shock waves produced by gamma-ray bursts can accelerate particles to cosmic ray energies exceeding 1015 electron volts, contributing to the galactic cosmic ray population that affects atmospheric chemistry and biological evolution on countless worlds. Dr. Luke Drury from the Dublin Institute for Advanced Studies, whose theoretical work addresses cosmic ray acceleration mechanisms, calculates that gamma-ray bursts may contribute significantly to the cosmic ray flux at the highest energies, creating a population of ultra-high energy particles that can travel across galactic distances and affect planetary environments throughout the Milky Way. The supermassive black hole growth implications suggest that gamma-ray bursts may influence the evolution of galactic centers. Some theoretical models propose that gamma-ray bursts in dense stellar environments can contribute material to central black holes while simultaneously clearing surrounding gas through radiation pressure. Dr. Mitchell Bagelman from the University of Colorado Boulder, whose research addresses black hole galaxy coevolution, observes that gamma-ray bursts occurring in galactic nuclei could provide both accretion material and feedback energy, potentially playing roles in the observed correlations between supermassive black hole masses and galactic properties. The galactic escape velocity considerations reveal that the most energetic gamma-ray burst, ejecta, can achieve velocities exceeding the escape speed of their host galaxies. Material accelerated to velocities approaching 10,000 kilometers per second can escape even from massive galaxies, distributing gamma-ray burst products into intergalactic space. Dr. Crystal Martin from UC Santa Barbara, whose observations probe galactic outflows, explains that gamma-ray burst-driven winds can enrich the circumgalactic medium with heavy elements, potentially affecting the chemical evolution of satellite galaxies and the broader cosmic web. The galaxy formation implications extend to the earliest epochs of cosmic evolution. During the first billion years after the Big Bang, when galaxies were smaller and less massive, Gamma-ray bursts may have been capable of disrupting entire galactic disks through their enormous energy release. Dr. Volker Braun from the University of Texas at Austin, whose research addresses the first stars and galaxies, notes that gamma-ray bursts from population 3 stars, the first generation of massive stars in the universe, could have played crucial roles in determining which protogalaxies survived to form the galactic populations we observe today. The metallicity gradient effects demonstrate how gamma-ray bursts can alter the spatial distribution of heavy elements within galaxies. The asymmetric ejection of our process material can create chemical inhomogeneities that persist for hundreds of millions of years, affecting subsequent generations of star formation. Dr. Ken Nomoto from the University of Tokyo, whose nucleosynthesis calculations address gamma-ray burst element production, calculates that single gamma-ray burst events can dominate the process element budget within volumes spanning several hundred parsecs, creating chemical signatures detectable in stellar populations formed millions of years after the original explosion. The radiation-driven outflows powered by gamma-ray bursts can also affect the gas content of entire galactic disks. The energy injection from multiple gamma-ray bursts can drive superbubbles to break out of the galactic plane, creating chimneys that allow hot gas to escape into the galactic halo. Dr. Sylvain Vallot from the University of Maryland, whose observations probe galactic winds and outflows, explains that cumulative gamma-ray burst activity over cosmic time may have played important roles in determining the gas retention efficiency of galaxies, particularly during epochs when burst rates were higher than observed today. The galactic consequences of gamma-ray bursts ultimately reveal these cosmic explosions as fundamental drivers of galactic evolution, simultaneously destroying existing structures while creating conditions for new star formation and chemical enrichment. Chapter 7. Temporal Implications. The temporal implications of gamma-ray bursts extend across cosmic history, from the millisecond scale physics governing their emission mechanisms to their potential roles in shaping biological evolution over hundreds of millions of years. These time-dependent effects reveal gamma-ray bursts as both witnesses to cosmic evolution and active participants in determining the habitability of the universe across vast temporal scales. The millisecond scale temporal structure provides direct insights into the physics operating near black hole event horizons. High-resolution observations reveal gamma-ray burst variability on timescales as short as 1 millisecond, suggesting that the emission regions are confined to scales comparable to the Schwarzschild radius of stellar mass black holes. Dr. Bing Zhang from the University of Nevada, Las Vegas, whose research addresses rapid variability in gamma-ray bursts, explains that millisecond variability requires emission regions smaller than 300 kilometers in diameter, comparable to the size scales where general relativistic effects become dominant for stellar mass black holes. The light-crossing time constraints impose fundamental limits on the size of the gamma-ray burst emission region. For variability timescales of t seconds, the emission region cannot exceed c times t in diameter, where c represents the speed of light. This causality requirement, combined with the observed luminosities, creates what physicists call the compactness problem. Energy densities so extreme that gamma-ray photons should interact with each other to produce electron-positron pairs, making the source opaque to its own radiation. Dr. Peter Masharos from Pennsylvania State University, who first identified this paradox, notes that the resolution requires relativistic motion with Lorentz factors exceeding 100, enabling the emission to escape through relativistic beaming effects. The second-to-minute scale duration patterns reveal fundamental differences between gamma-ray burst progenitor systems. Long-duration bursts, typically lasting 2 to 1,000 seconds, correlate strongly with the formation of stellar mass black holes through core collapse of massive stars. Short-duration bursts lasting less than 2 seconds result from the merger of compact objects like neutron stars or neutron star black hole binaries. Dr. Krissa Cavallio-II from George Washington University, whose research established this bimodal distribution, observes that the temporal classification reflects the fundamental physics governing energy release in these different progenitor scenarios, with accretion timescales determining the duration of observable emission. The years to decades timescale reveals the long-term evolution of gamma-ray burst remnants and their interaction with surrounding material. Afterglow observations spanning multiple years show that the forward shock continues propagating through the interstellar medium long after the initial gamma-ray emission, gradually decelerating as it sweeps up increasing amounts of ambient material. Dr. Ido Berger from Harvard University, whose long-term monitoring campaigns track afterglow evolution, explains that the late-time afterglow provides crucial information about the energetics and geometry of the original explosion, while also probing the density structure of the circumstellar environment shaped by the progenitor star's evolution. The centuries to millennia timescale encompasses the propagation of gamma-ray burst shock waves across interstellar distances and their impact on molecular cloud chemistry. The passage of these shocks can alter the ionization state of molecular gas, affecting star formation rates and chemical evolution processes across galactic neighborhoods. Dr. Marco Spans from the University of Groningen, whose research addresses the impact of astrophysical shocks on molecular chemistry, calculates that gamma-ray burst shock waves can modify molecular abundances in giant molecular clouds for thousands of years, potentially affecting the initial conditions for planetary system formation in subsequently formed stellar systems. The million-year timescale reveals the demographic evolution of gamma-ray burst populations and their correlation with cosmic star formation rates. Statistical studies show that the gamma-ray burst rate has evolved significantly over cosmic time, with peak rates occurring when the universe was 2 to 4 billion years old, during the epoch of maximum star formation. Dr. Paul Jacobson from the University of Iceland, who surveys probe gamma-ray burst rate evolution, notes that the temporal evolution of gamma-ray burst rates provides unique constraints on the formation and evolution of massive stars across cosmic history, particularly for the metal-poor stellar populations that dominated early universe star formation. The 100 million year timescale encompasses potential correlations between gamma-ray burst activity and mass extinction events in Earth's biological history. Paleontological evidence suggests that several major extinctions may correlate temporally with enhanced cosmic ray fluxes or atmospheric chemistry modifications consistent with gamma-ray burst irradiation. Dr. Brian Thomas from Washburn University, whose research addresses the biological effects of astrophysical radiation, explains that gamma-ray bursts occurring within our galactic neighborhood could trigger extinction events by depleting stratospheric ozone and exposing surface life to enhanced ultraviolet radiation, with effects persisting for decades to centuries following the initial burst. The billion-year timescale reveals gamma-ray bursts as potential regulators of cosmic habitability through their cumulative effects on galactic chemical evolution and atmospheric processing. Over the age of the universe, gamma-ray burst activity may have preferentially affected certain galactic environments, creating habitability gradients that influence where complex life can develop and persist. Dr. James Annes from Fermilab, whose research addresses the galactic habitable zone, proposes that gamma-ray burst activity may have created a galactic habitable zone, regions where planets can maintain stable atmospheres and surface conditions necessary for complex life development over geological timescales. The cosmic time implications extend to the role of gamma-ray bursts as probes of the early universe and the first generation of stars. Because gamma-ray bursts can be detected from cosmological distances, they provide observational access to epochs when the universe contained very different stellar populations and galaxy morphologies. GRB 090423 occurring when the universe was only 630 million years old, offers insights into stellar death processes during the epoch of reionization, when the first stars were transforming the universe from a neutral to an ionized state. The temporal correlations with gravitational wave detections open new possibilities for studying compact object merger rates across cosmic history. The detection of GW170817 and its associated gamma-ray burst, GRB170817, demonstrated that neutron star mergers produce both space-time ripples and electromagnetic signals, enabling multi-messenger studies of these cosmic collisions. Dr. Mansi Kasliwal from Caltech, whose research focuses on electromagnetic counterparts to gravitational wave sources, explains that temporal correlations between gravitational waves and gamma-ray bursts enable precise measurements of Hubble's constant and provide new tests of general relativity under extreme conditions. The progenitor evolution timescales reveal how gamma-ray burst rates depend on the metallicity and age of stellar populations. Massive stars in metal-poor environments can more easily maintain the rapid rotation necessary for gamma-ray burst production, because stellar winds are less efficient at removing angular momentum. This metallicity dependence suggests that gamma-ray burst rates were higher in the early universe when heavy element abundances were lower. Dr. Marco Spera from the University of Padova, whose stellar evolution calculations address gamma-ray burst progenitors, notes that the temporal evolution of gamma-ray burst rates reflects the changing chemical composition of star-forming regions across cosmic time, with implications for understanding stellar feedback and galaxy evolution. The recurrence timescales within individual galaxies reveal gamma-ray bursts as episodic but recurring phenomena that can repeatedly affect galactic environments. Current estimates suggest that Milky Way-sized galaxies experience gamma-ray bursts approximately once every 100,000 to 1 million years, with the exact rate depending on the galaxy's star formation, history, and metallicity. Evolution. Dr. Andrew Levin from the University of Warwick, whose research addresses gamma-ray burst host galaxy properties, calculates that over the age of the universe, our galaxy has likely experienced several hundred gamma-ray bursts, with potentially significant cumulative effects on atmospheric chemistry and biological evolution. The detection latency effects reveal how gamma-ray burst temporal properties depend on observational capabilities and selection effects. Current gamma-ray burst detectors are most sensitive to events lasting seconds to minutes, potentially missing very short or very long duration events that could reveal additional physics or progenitor populations. Dr. Neil Garrels, former principal investigator for NASA's SWIFT mission, observed that our understanding of gamma-ray burst temporal properties remains limited by instrumental capabilities, with space-based detectors providing access to gamma-ray wavelengths that cannot penetrate Earth's atmosphere. The temporal implications ultimately reveal gamma-ray bursts as cosmic phenomena that operate across all relevant timescales in the universe, from the fundamental physics timescales governing black hole formation to the billion-year timescales characterizing galactic evolution and biological development. Chapter 8. Detection Methods. The detection of gamma-ray bursts requires overcoming extraordinary technical challenges, from capturing gamma rays that cannot penetrate Earth's atmosphere to localizing fleeting cosmic flashes with sufficient precision for follow-up observations. The evolution of detection methods over 5 decades reveals how advancing technology has transformed our understanding of the universe's most energetic phenomena. The fundamental detection challenge stems from the nature of gamma radiation itself. Gamma rays, being high-energy electromagnetic radiation, interact strongly with matter and cannot penetrate Earth's atmosphere. Unlike optical astronomy, which benefits from atmospheric transparency, gamma-ray astronomy requires space-based observatories operating above the protective barrier that shields us from cosmic radiation. Dr. Neil Garrels, who led NASA's SWIFT mission until his death in 2017, explained that gamma-ray detection requires us to place our instruments in the most hostile environment humans have ever accessed, the vacuum of space, where detectors must operate flawlessly for years without maintenance while subjected to temperature extremes and radiation damage. The detection principle relies on the interaction of gamma rays with detector materials through three primary mechanisms: photoelectric absorption, Compton scattering, and pair production. For gamma-ray burst energies typically ranging from 10 keV to 10 MeV, Compton scattering dominates, requiring detector systems that can measure the energy and direction of scattered photons with high precision. Dr. Valerie Connaughton from the University of Alabama in Huntsville, whose expertise spans gamma-ray detector development, notes that modern gamma-ray burst detectors must simultaneously optimize for sensitivity, temporal resolution, and angular resolution while operating in the harsh radiation environment of space. The early detection methods relied on relatively simple scintillation detectors aboard military surveillance satellites. The Vela satellites, launched during the 1960s, use cesium iodide crystals that emit visible light when struck by gamma rays. These early detectors could determine burst timing and rough energy spectra but provided no directional information, limiting follow-up observations and preventing distance determinations. Dr. Ray Kledesettle, who led the team that first identified gamma-ray bursts in Vela data, recalls that the early detectors were designed for nuclear weapons monitoring, not astrophysics, so extracting cosmic ray burst properties required considerable ingenuity in data analysis. The breakthrough in localization capability came with the Burst and Transient Source Experiment, BATS, aboard the Compton Gamma Ray Observatory. Launched in 1991, BATS's 8 detectors, positioned to provide all-sky coverage, could localize gamma-ray bursts to within several degrees by comparing the relative intensities recorded by different detectors. Dr. Jerry Fishman from NASA Marshall Space Flight Center, BATS's principal investigator, explains that BATS's triangulation method enabled statistical studies of gamma-ray burst distributions, revealing their isotropic sky distribution and establishing that they originated from cosmological distances rather than our galactic neighborhood. The temporal resolution requirements demand detection systems capable of millisecond-scale measurements. Modern gamma-ray burst detectors like the gamma-ray burst monitor aboard the Fermi Space Telescope achieve temporal resolution as fine as 64 microseconds, enabling detailed studies of rapid variability that provide insights into emission mechanism physics. Dr. Colin Wilson-Hodge from NASA Marshall Space Flight Center, who manages GBM operations, notes that the rapid variability observed in some gamma-ray bursts requires timing precision comparable to atomic clocks, enabling studies of causality and emission region sizes near black hole event horizons. The energy resolution capabilities have evolved to enable detailed spectral analysis of gamma-ray burst emission. The Fermi Large Area Telescope can measure gamma-ray energies from 20 MeV to over 300 GeV, with energy resolution better than 10% for high-energy photons, revealing spectral features that constrain emission mechanisms and provide tests of fundamental physics. Dr. Julie McHenry, Fermi Project scientist, explains that high-energy gamma-ray detection enables studies of particle acceleration and relativistic shocks, while providing tests of Lorentz invariance and constraints on quantum gravity theories. The multi-wavelength coordination represents a crucial advancement in gamma-ray burst detection methodology. NASA's SWIFT satellite, launched in 2004, revolutionized the field by providing rapid, autonomous follow-up observations across X-ray, ultraviolet, and optical wavelengths within seconds of gamma-ray burst detection. Dr. Judith Rakison from NASA Goddard Space Flight Center, whose research focuses on multi-wavelength afterglow properties, observes that SWIFT's rapid response capability enables observations of early afterglow phases that were previously inaccessible, revealing the transition from prompt gamma-ray emission to longer-lived afterglow radiation. The ground-based follow-up networks demonstrate international coordination in gamma-ray burst science. The Gamma-ray Coordinates Network, GCN, operated by NASA, distributes rapid burst localizations to observatories worldwide, enabling ground-based telescopes to begin afterglow observations within minutes of space-based detection. Dr. Scott Barthelme, who manages the GCN system, explains that the real-time coordination between space-based gamma-ray detectors and ground-based optical telescopes enables comprehensive studies spanning 15 orders of magnitude in photon energy, from radio waves to high-energy gamma rays. The automated detection algorithms must distinguish genuine cosmic gamma-ray bursts from instrumental backgrounds and terrestrial interference sources. Modern detection systems employ sophisticated pattern recognition software that can identify burst characteristics within seconds and automatically trigger follow-up observations. Dr. Adam Goldstein from the University's Space Research Association, who develops burst detection algorithms, notes that automated burst identification must operate reliably in space environments where cosmic ray interactions create continuous background signals that can mimic genuine astrophysical events. The angular resolution limitations represent ongoing challenges in gamma-ray burst astronomy. Unlike optical telescopes, which can achieve sub-arcsecon resolution, gamma-ray instruments typically provide localizations accurate to degrees or arcminutes. The Fermi Large Area Telescope achieves the best current gamma-ray angular resolution of approximately 0.1 degrees for high-energy photons, but this still encompasses thousands of potential host galaxies for distant bursts. Dr. Nicola Omade from Stanford University, whose research focuses on high-energy gamma-ray astronomy, explains that improving gamma-ray angular resolution requires larger detector areas and more sophisticated reconstruction algorithms, pushing the limits of space-based instrumentation. The sensitivity thresholds determine which gamma-ray bursts can be detected across cosmological distances. Current space-based detectors can identify bursts with peak fluxes as low as 10-8 erg-cm2s1, enabling detection of typical bursts out to redshifts exceeding 6 when the universe was less than 1 billion years old. Dr. Peter Veers from the University of Alabama in Huntsville, whose research addresses gamma-ray burst detection statistics, calculates that current detector sensitivities enable observation of roughly 1,000 gamma-ray bursts per year, representing a small fraction of the total population occurring throughout the observable universe. The spectral coverage requirements span enormous energy ranges to capture the full gamma-ray burst phenomenon. The combination of Swift's Burst Alert Telescope 1515 OKEV, Fermi's Gamma-Ray Burst Monitor 8 keV to 40 MeV, and Fermi's Large Area Telescope 20 MeV to 300 JeV provides continuous spectral coverage spanning nearly 6 orders of magnitude in photon energy. Dr. Michael Briggs from the University of Alabama in Huntsville, whose research focuses on gamma-ray burst spectroscopy, observes that broad spectral coverage reveals that gamma-ray bursts emit across the entire electromagnetic spectrum, requiring coordinated observations from multiple detector systems to capture their full energy output. The polarization measurement capabilities represent the next frontier in gamma-ray burst detection methodology. The recently launched Ichira spacecraft achieved the first detection of gamma-ray burst polarization, while proposed missions like the polarimetry of relativistic ejecta from gamma-ray bursts, POLAR, aim to provide systematic polarization measurements. Dr. Nicolas Pradouet from the University of Geneva, principal investigator for the POLAR experiment, explains that polarization measurements provide unique insights into magnetic field structure and geometry within gamma-ray burst jets, enabling tests of theoretical models that cannot be constrained through flux and spectral measurements alone. The gravitational wave correlation capabilities, demonstrated by the LIGO Virgo Fermi detection of GW170817, GRB 170817A, open new possibilities for multi-messenger gamma-ray burst astronomy. The precise timing correlation between gravitational wave and electromagnetic signals provides unprecedented constraints on general relativity and neutron star physics. Dr. Nelson Christensen from Carleton College, whose research addresses gravitational wave data analysis, notes that coordinated gravitational wave and gamma-ray burst observations enable measurements of fundamental physics under conditions that cannot be replicated in terrestrial laboratories. The future detection capabilities will likely involve constellation missions, providing improved sky coverage and rapid localization accuracy. Proposed missions like the Black Hole and Neutron Star High Energy Survey, BENS, and the Gamma Ray and Antimatter Survey, GRAMS, aim to achieve arc-minute scale localizations while maintaining high sensitivity across broad energy ranges. Dr. Georgia Dinolfo from NASA Goddard Space Flight Center, whose research addresses future gamma-ray mission concepts, explains that next-generation gamma-ray burst detectors will combine improved sensitivity with rapid localization capabilities, enabling real-time multi-messenger follow-up observations that could revolutionize our understanding of compact object physics. The detection methods ultimately reveal gamma-ray bursts as cosmic phenomena that push observational technology to its limits while providing unique laboratories for testing fundamental physics under the most extreme conditions accessible to human observation. Chapter 9. Cosmic Perspective. From the vantage point of cosmic perspective, gamma-ray bursts represent far more than stellar death events. They are fundamental organizing principles of the universe, cosmic mechanisms that regulate galactic evolution, determine the distribution of heavy elements, and potentially control where complex life can emerge across the cosmos. This perspective reveals the profound interconnectedness between the most violent phenomena in nature and the delicate conditions necessary for biological complexity. The cosmic energy budget places gamma-ray bursts among the universe's most significant energy sources. While individual stars like our Sun release their energy gradually over billions of years, the cumulative energy output of gamma-ray bursts across cosmic history rivals that of all stellar fusion combined. Dr. Abraham Loeb from Harvard University, whose research spans theoretical astrophysics and cosmology, calculates that gamma-ray bursts have contributed roughly Y joules to the cosmic energy budget since the first stars formed, equivalent to the total nuclear binding energy of all atoms in millions of galaxies. The universal distribution reveals gamma-ray bursts as truly cosmic phenomena, occurring across all observed epochs of cosmic history and in galaxies spanning the full range of masses, morphologies, and environments. The fact that gamma-ray bursts can be detected from the edge of the observable universe, when light from these events began its journey toward us more than 13 billion years ago, means we are witnessing stellar death processes that occurred when the universe was fundamentally different from its current state. The metallicity connections illuminate how gamma-ray bursts serve as archaeological tools for understanding cosmic chemical evolution. Long-duration gamma-ray bursts preferentially occur in metal-poor star-forming regions, reflecting the conditions necessary for massive stars to maintain the rapid rotation required for jet formation. Dr. Andrew Levin from the University of Warwick, whose observations probe gamma-ray burst host galaxy properties, explains that gamma-ray burst locations trace the cosmic evolution of stellar populations, providing unique insights into star formation processes during epochs when the universe contained very different chemical compositions. The habitability implications suggest that gamma-ray bursts may define a cosmic habitability function, determining which regions of the universe can support the long-term stability necessary for complex biological evolution. The combination of sterilization effects and heavy element production creates a complex relationship where gamma-ray bursts simultaneously threaten existing life while providing the materials necessary for planet formation. Dr. Brian Thomas from Washburn University, whose research addresses astrobiology implications of high-energy astrophysics, notes that gamma-ray bursts may create a galactic habitable zone where planets can maintain stable atmospheres over geological time, similar to how stellar luminosity defines habitable zones around individual stars. The temporal perspective reveals gamma-ray bursts as cosmic clocks, marking significant transitions in universal evolution. The peak gamma-ray burst rate occurred when the universe was 2 to 4 billion years old, coinciding with the epoch of maximum star formation and the transition from a universe dominated by small, irregular galaxies to one containing the massive spiral galaxies we observe today. Dr. Paul Jacobson from the University of Iceland, whose surveys trace gamma-ray burst rate evolution, observes that the cosmic gamma-ray burst rate provides a direct measure of how massive star formation has evolved throughout cosmic history, revealing periods when stellar violence peaked across the observable universe. The dark matter connections emerge through gamma-ray burst studies of galaxy formation and large-scale structure evolution, because gamma-ray bursts trace massive star formation in young galaxies. They provide observational probes of how dark matter halos assemble and merge throughout cosmic time. Dr. Massimo Della Valle from IN of Capodimonte Observatory, whose research addresses gamma-ray burst cosmology, explains that gamma-ray bursts occurring in the early universe provide unique constraints on dark matter halo assembly, revealing how the cosmic web's growth influenced the first episodes of star formation and galactic evolution. The cosmic web perspective places gamma-ray bursts within the largest structures in the universe, the filaments and nodes of dark matter and gas that define cosmic architecture on scales exceeding 100 million light-years. Gamma-ray burst shock waves can propagate beyond individual galaxies to affect the circumgalactic medium and potentially influence gas flows along cosmic web filaments. Dr. Crystal Martin from UC Santa Barbara, whose research addresses galactic outflows and their environmental effects, notes that the most energetic gamma-ray bursts can drive material into the intergalactic medium, potentially affecting cosmic web evolution and the process of galaxy formation across cosmological volumes. The fundamental physics perspective reveals gamma-ray bursts as natural. Laboratories where extreme conditions enable tests of physical theories but cannot be performed in terrestrial experiments. The combination of strong gravitational fields, relativistic velocities, and intense magnetic fields creates conditions where quantum field theory, general relativity, and plasma physics operate simultaneously at their most extreme limits. Dr. Dimitrios Giannios from Purdue University, whose theoretical work addresses relativistic astrophysics, explains that gamma-ray bursts provide the only accessible laboratories where we can study physics under conditions approaching those near black hole event horizons, enabling tests of fundamental theories under extreme conditions. The quantum gravity implications emerge through observations of high-energy gamma-ray photons that have traveled cosmological distances. Theoretical models predict that quantum gravitational effects might cause slight delays in the arrival times of photons with different energies, providing tests of Lorentz invariance and quantum gravity theories. Dr. Floyd Stecker from NASA Goddard Space Flight Center, whose research addresses fundamental physics tests using gamma-ray observations, notes that gamma-ray bursts serve as cosmic laboratories for testing whether the fundamental constants of nature remain truly constant across cosmic time, and whether space-time itself exhibits discrete rather than continuous structure. The information perspective reveals gamma-ray bursts as cosmic messengers, carrying information about conditions in the most extreme environments accessible to observation. The spectral properties, temporal structure, and polarization characteristics of gamma-ray emission encode details about magnetic field strengths, particle energies, and geometries near black hole event horizons. Dr. Bing Jiang from the University of Nevada, Las Vegas, whose research addresses gamma-ray burst physics across multiple scales, observes that each gamma-ray burst represents a cosmic experiment in extreme physics, providing observational data about conditions where classical physics breaks down and quantum effects become dominant. The evolutionary perspective places gamma-ray bursts within the broader context of cosmic evolution, from the formation of the first stars through the development of mature galactic systems capable of supporting complex chemistry and biology. The decline in gamma-ray burst rates since the peak of cosmic star formation suggests that the universe has evolved beyond its most violent phase, potentially creating more stable conditions for biological evolution. Dr. Rosalba Perna from Stony Brook University, whose research addresses gamma-ray burst evolution and environmental effects, explains that the cosmic evolution of gamma-ray burst rates may reflect the universe's transition from a chaotic, violent youth to a more stable maturity where complex structures can develop and persist. The anthropic perspective considers whether the observed properties of gamma-ray bursts reflect selection effects related to the existence of observers. The fact that Earth has apparently avoided sterilization by nearby gamma-ray bursts throughout its 4.6 billion year history may reflect either statistical fortune or fundamental constraints on where complex life can develop. Dr. James Annis from Fermilab, whose research addresses the galactic habitable zone, proposes that our existence as observers may itself constrain the frequency and proximity of gamma-ray bursts, suggesting that universes with very different gamma-ray burst properties might be less likely to develop complex life capable of studying cosmic phenomena. The holistic perspective integrates gamma-ray bursts into our understanding of cosmic complexity, how the universe evolves from simple initial conditions toward increasingly complex structures capable of information processing, self-organization, and ultimately consciousness. The role of gamma-ray bursts as both destructive and creative forces suggests they may be essential elements in the cosmic evolution toward complexity. Dr. Eric Chasen from Harvard University, whose research addresses cosmic evolution and complexity, observes that gamma-ray bursts represent crucial transitions in cosmic evolution, converting gravitational potential energy into electromagnetic radiation while simultaneously creating the chemical diversity necessary for complex molecular systems. The ultimate cosmic perspective reveals gamma-ray bursts as expressions of the universe's fundamental creativity, its capacity to generate phenomena that transcend human imagination while operating according to mathematical principles we can discover and understand. Each gamma-ray burst represents a moment when the universe demonstrates its ability to concentrate unimaginable energies into fleeting displays of cosmic artistry that simultaneously destroy and create, ending stellar lives while forging the materials necessary for new generations of stars, planets, and potentially life itself.